Okay. Hi, everyone. Thanks for being here today. My team and I are going to present on different strategies for improving the moisture barrier properties of polymailers, of seaweed-based polymailers. So meet our team. My name is Annika Ramona, and I'm a second-year MPH candidate in environmental health sciences.
I'm Scarlett Kilpatrick. I'm a third-year PhD student in environmental engineering.
I'm Isabel Araldi. I am also a second-year MPH student in environmental health sciences.
I'm Joe Ondas. I'm a chemistry MS student.
I'm Emma Sage. I'm also a second-year environmental health sciences MPH candidate.
I'm Ari. I'm also a second-year environmental health sciences MS candidate.
Okay, so here is a roadmap of our presentation today, showing everything that we're going to be discussing. Our background will provide an overview of our challenge, our partner organization, and our bad actor. Our approach will dive into our project requirements and the 4 categories that we split our strategies into. The inspiration will explain the context about each strategy we selected from each of our 4 categories. Our technical performance section will dive into the mechanical requirements of the product and the water barrier and biodegradability metrics. The health performance will talk about the environmental and human health impacts of each strategy. And then we'll wrap up with our conclusion and next steps. So some background, Sway, our partner organization, is a Bay Area startup. They manufacture seaweed-based thin film as an alternative to traditional LDPE-based packaging, which is a type of plastic. And my team and I were challenged with finding a solution to improve the moisture barrier properties of Sway's seaweed-based polymailers. Sway's formula currently includes hot water, powdered seaweed, and plant-based additives. And then it is blended and molded into the polymailers. Currently, Sway's polymailers are highly hydrophilic. They swell by 200% when they're wet, which is not practical when they need to be used for shipments. So traditional polymailers are manufactured with LDPE, or low density polyethylene, which is a polymer and type of plastic that's used for malleable plastic items like packaging, squeeze bottles, and single-use water bottles. LDPE can be compared to HDPE, or high density polyethylene, which is used for more rigid and durable plastics like reusable water bottles. In this figure, you can see the structural differences between HDPE and LDPE. The branching in LDPE mean that its molecules are less tightly packed and less crystalline, which gives it a lower density. And because it's a polymer, it is also hydrophobic. So the structural qualities of LDPE that give it its hydrophobicity, durability, and flexibility allow it to perform really well for items like polymailers. Okay, so it's important to note that LDPE is recyclable. However, a 2020 study found that plastic packaging, found that plastic manufactured since the 50s has mostly not been recycled. So less than 2% has been recycled, and less than 6% has been incinerated, and approximately 92% has turned up in landfills or in the environment. And because most plastic doesn't get recycled or recycled properly, it's really important to pivot to a more biocompatible alternative going forward. And for as recycling LDPE specifically, in theory, it can be recycled and combined with new LDPE or used on its own to create new products. However, in practice, it often is not actually recycled and recovered. And according to a 2009 study, it has very poor recovery rates. And most LDPE post-consumer packaging is not recovered, and it ends up in landfills or in the environment.
So we consulted with Sway to assess their priorities and determine the framework and constraints of our approach. So central to Sway's mission is that their product must be 100% bio-based and compostable by both home and industrial standards. So this is measured by the percent carbon dioxide conversion over time listed here. And field tests of Sway's current material suggest that it completely disintegrates within 48 days. So this places their current product well below these listed cutoffs, which is a great point to highlight and consider because each of our proposed solutions vary in the extent to which they alter biodegradation rates, but their starting product is well below these goals, and the hope is to keep it that way. We also are not going to be able to provide specific quantitative metrics for a percent carbon dioxide conversion for each alternative, since the exact conversion is going to depend on the exact formulation of the complete product material. So instead, we're going to discuss how each component is likely to affect these base carbon conversion rates in general. Secondly, their product has to be non-petroleum based. So we only considered any alternatives that were completely free of any petroleum derivatives. And all of our alternatives have to be responsibly sourced, and they have to meet the minimum mechanical requirements to function as a polymailer and optimize water barrier properties. It's worth noting, and it will be discussed further, that LDPE might be over-engineered for this purpose as a polymailer. So we consulted with Sway to set alternate technical benchmarks that are more reasonable to achieve. These tenets here framed our approach as we compiled possible candidates for barrier property and assessed how they might alter the existing mechanical properties from Sway's current technology. So as you'll learn, there are some trade-offs between improvements in one property and setbacks in another, water barrier and biodegradability being an important example here. So all of these trends that we're going to highlight should be considered with respect to Sway's current technology, as slight decreases in certain properties might not be a problem if they're paired with proper improvements in key things that we're considering.
So because Sway's formula for their polymailer is proprietary, they have suggested that we look at these three proxies, these three hydrocolloids to use as proxies because they are also sourced from seaweed. One thing to note about their structure is that they have a lot of hydroxyl groups, which means that they're pretty hydrophilic. And this is why Sway is having so many issues with their water barrier performance. And this is the issue that we are trying to fix.
Okay, so in order to narrow down the strategies that we'll be presenting to you, we broke our search up into 4 main groups. So we have minerals, waxes and lipids, polyesters, and crosslinkers is kind of our big overarching strategies. We split up into pairs and kind of went and researched each of these overarching categories. And each pair kind of brought back to the group the most viable strategies that they found based on the literature and based on performance metrics that were reported. What we ended up settling on were silica nanoparticles as an additive and montmorillonite clay as an additive under our minerals category. We chose a beeswax additive for our waxes and lipids category, polylactic acid coating for polyesters, and then a chitosan and ferulic acid combination additive for our crosslinkers category. So to go into our inspiration, the way this presentation will be structured is we'll go through inspiration for each of these categories, and then we'll do technical performance and environmental performance in that same order. So for montmorillonite clay, this is a major component of bentonite, and bentonite is a natural clay that's formed when volcanic ash mixes with water. Bentonite has many different usages. It's been used to line landfills and seal water wells because of its ability to reduce water vapor transmission rate, and this contains montmorillonite clay. And MMT, which is the abbreviation that we'll use, is one of the most commonly used particles in biopolymer-based nanocomposites. And we saw that in the literature that we found. And then our other alternative is silica nanoparticles. Silica is one of the most common elements on Earth. It is commonly found in nature as quartz, but it's also found in plants, particularly in rice husks. And there's a lot of research going into how we can sustainably extract silica from rice husks and other agricultural byproducts. Currently, it is used in railroad track and floor coatings, paints and glazes, and as a binding agent. So there's precedent to using this as some kind of sealing agent. And there is also a really promising study that shows that silica nanoparticles were used to enhance the hydrophobicity of a cassava starch film. So for our waxes and lipids category, we settled on beeswax as our most viable alternative. We did look at some other waxes. So we looked at paraffin wax, which we ruled out due to its derivation from petroleum. We also looked at carnauba wax, which is cheaper than beeswax, but has less ideal technical performance metrics. And there are also some concerns with the sourcing of carnauba wax, as it's been shown to be linked to deforestation and loss of biodiversity. And we also looked at candelilla wax, but found that it was a bit more brittle, with worse moisture barrier properties and cost about the same amount as beeswax. So beeswax is secreted by bees, as most of you probably know, to form the structure of honeycomb, which is where bees store honey. It has high plasticity and it protects against moisture loss, corrosion, and abrasion. And humans have been using beeswax for a very long time. The first recorded usage was 1550 BC. And today it's still used in a variety of products, including different coatings, varnishes, and polishes. And there are actually reusable and compostable beeswax food wraps currently available on the market. Bees are also really important crop pollinators, so there are ecological co-benefits to this strategy. We found a study that showed that raising bees accounts for $15 billion in added crop value, which is worth about 10 to 20 times the value of just the products of beeswax and honey. So for looking at polyesters, we chose PLA, polylactic acid. This is a synthetic alternative, which is derived from fermenting simple sugars from biomass, so corn and cassava. It is also used for food packaging, bottles, cold drink cups, and different films. So there is, again, a precedent to using this as kind of a bioplastic alternative. It is processed at the industrial level, and it uses the same technology as traditional petroleum-based thermoplastics, which makes it economically competitive. And there is a lot of research into this strategy going on right now into copolymerization and blending approaches to improve the performance of PLA. So looking at our cross-linkers, ferulic acid is found in plants. It cross-links to reinforce cell walls and block infection. It can be extracted from agricultural waste, particularly maize, rice, and wheat bran. And it has current applications in food preservation due to its cross-linking activity. And then chitosan, which is what we'll be combining with ferulic acid. So it is derived from chitin, which is the second most abundant natural component natural compound after cellulose. And it is found in exoskeletons and cell walls. And chitosan is produced by deacetylating chitin. And chitin can be obtained from feedstock, so byproducts of crab, insect, shrimp production, kind of any arthropods that have an exoskeleton. And chitosan is already used in food packaging and films. Like PLA, there's a lot of research into how we can combine chitosan with other things to improve its performance. So we're excited about this combination.
So to complete our technical performance of all of our potential enhancements, we identified the key metrics for necessary functioning as a polymailer. Our properties fall into two broad categories relating to the mechanical strength and the water barrier properties. For each metric, Sway gave us a target summarized in this table here, and we look at LDPE side by side here to emphasize the fact that particularly when it comes to the water barrier properties, LDPE is hard to beat. However, LDPE doesn't have to be our benchmark, as lower metrics can also achieve the desired functionality for this end use. Elastic modulus, strain at the break, and tensile strength all directly relate to the durability of the packaging. And then the water barrier metrics are all vital to the material maintaining that aforementioned mechanical integrity, as well as serving as an important protection for anything contained inside the mailer. The water vapor transmission rate is our most important water barrier benchmark that we considered, and it's defined as the rate at which water vapor permeates through a film at set conditions of temperature and relative humidity. It's worth noting that we back calculated this number from all of our various studies, as it is film specific and related to the broader category of water vapor permeability. And we converted everything to the units of grams per 100 inches squared here, since that were the units that SWAY provided to us for our target, and we wanted it to map on as easily as possible. The water contact angle then is a measure of hydrophobicity. So generally speaking, a water contact angle greater than 90 degrees defines a hydrophobic surface. And then the swelling and the water solubility are other important properties identified by SWAY to ensure that the mechanical integrity of the material is maintained over time, as of course, swelling and dissolution would weaken all of the above properties. As mentioned previously, most bioplastic producers have the most trouble meeting these water barrier benchmarks, as in many cases, there's a direct trade-off between water barrier and biodegradability. So for all of our technical comparisons, we report the specified values outlined in each paper that we ultimately chose as our key paper for each category. And we also calculated percent increase or decrease of each as compared to the reference material. So each study that we considered has a different base composition, which is generally some combination of our proxies mentioned earlier, which is also likely going to be different from SWAY's proprietary material. So therefore, we find it most useful in presenting an opportunity roadmap to summarize how each potential addition changes from the unique baseline in consideration. We color-coded this, and specifically, those with the best percent improvement from the baseline are the darkest green. Those the most detrimental are the darkest red. So this should allow for identification of the most important considerations based on SWAY's current starting formulation. In the mineral category, as mentioned, we identified two potential candidates for additions: montmorillonite, which is an aluminosilicate clay mineral, and silica nanoparticles. Both enhancements are going to be incorporated similarly into the matrix, where the minerals are first dissolved in water and then mixed into an aqueous solution of agar, whatever else, and plasticizers. And 1 to 3% by weight is a common choice for such addition. So both materials show significant improvements from the baseline, notably with respect to the water barrier. And it's also worth noting that while only the silica nanoparticles increase the water contact angle, while montmorillonite actually decreases it, both materials still improve the overall water vapor transmission rate, which is the more important consideration here. And this can be explained mechanistically by the fact that the silica nanoparticles directly improve the water barrier by making the surgery more hydrophobic, as silica can occupy hydrogen bonding sites on the surface where water would otherwise bind. While on the other hand, montmorillonite is a hydrophilic substance, but the small particles dispersed in the polymer matrix increase the overall path tortuosity that the water has to flow through, and thus the associated rate of water diffusion. So they're incorporated similarly, and they achieve similar end goals in increasing water vapor transmission rate, but they do so by a different mechanism.
So for our waxes and lipids strategy, we're focusing on beeswax as an additive to increase the hydrophobicity of the film. In the study that we present in this table, they were looking at how increasing the concentration of beeswax in their agar and maltodextrin emulsion film could enhance the mechanical and barrier properties. To make these films, they blended together agar and maltodextrin and added 10 and 20% beeswax by weight into the solution. And then they used the casting method to actually form the films. However, one thing to note is that the authors did report that the films were pretty irregular and heterogeneous because some phase separation occurred between the nonpolar beeswax and the polar film matrix. However, despite this phase separation, as you can see in this table, there were major enhancements in the properties, or in the performance, of the film for all categories. And especially for the 20% beeswax film, they saw major improvements for all the mechanical properties, as well as for the water contact angle, and then some moderate improvements for the remaining barrier properties. I do want to note that we're presenting water vapor permeability, not water vapor transmission rate in this table, because we didn't have the necessary measurements in order to make that conversion. So therefore, we can't really compare that metric across strategies. So for our polyester strategy, we're focusing on PLA as a coating to act as a protective barrier for the films. The study that we present in this table looked at how PLA lamination could enhance the properties of their nanocomposite films, which consist of agar, carrageenan, and 5% nano clay. In this study, they also use the casting technique to form the films. They have a double layer, which is just the nanocomposite film coated on one side with the PLA, and then the triple layer film is referring to the nanocomposite film coated on both sides with the PLA. And hydrogen bonding is what is allowing these layers to stick together. So we see the greatest improvements for the triple layer film in the strain at break, the water vapor transmission rate, and for the swelling. And then there are also moderate improvements for the water contact angle and for the water solubility. But unfortunately, they did report a pretty large decrease in the tensile strength performance.
All right, so moving on to our final strategy addressed here, the use of cross-linkers to improve moisture barrier properties. So this chart or table is based off a study in which chitosan and sodium alginate were cross-linked via ferulic acid, and these mechanical and water barrier metrics were assessed. Some things to note were there's a 1-to-1 ratio of chitosan and sodium alginate utilized. You'll notice too that there are, on the far right, the percent change, there's two different data points provided. CTS ferulic acid, or CTS FA-SA, is our chitosan sodium alginate cross-linked with ferulic acid. This is synthesized via direct mixing of all of the components at once. Furthermore, they explore this LBL one, which is a layer-by-layer synthetic approach in which the sodium alginate layer is first cast, allowed to dry, and then a chitosan ferulic acid mixture is spread across the top of that and then allowed to dry furthermore. Some things to note here is that we see water barrier metrics are vastly improved when a layer-by-layer approach is utilized. This is thought to occur, and I should say the same occurs for tensile strength. This is thought to occur as the layer-by-layer approach allows a greater surface contact between the two layers, resulting in a denser structure. Furthermore, the same can be said for utilization of ferulic acid. If we compare it to the baseline reference, we can see that there is an improvement in our water barrier metrics that once again can be associated to a denser structure. Ferulic acid and generally cross-linkers in general act to create a denser structure as they draw together the polymer chains. In this case, we can visualize that ferulic acid can cross-link these two polymers via hydrogen bonding with sodium alginate and electrostatic interactions with the chitosan, hence our inclusion of chitosan in this suggestion. So, sorry, it's... Thank you. Oh, there we go. Awesome. Sorry about that. So just summarizing all of our technical performance, that way we can view them side by side and make better comparisons. What we have shown here are the percent changes. As was previously mentioned, just giving the raw data isn't going to be as helpful as these aren't directly based off Sway's system. Rather, we can look at how these additives or coatings improve the properties. So just at a quick glance, we can see that our agar maltodextrin with the 20% weight beeswax additive has the most beneficial improvements with no observed adverse effects to any other metrics we collected. What is also visualized and what's important to mention is that these strategies shouldn't be considered in a vacuum. Rather, they should be considered as having potential to be combined with other strategies. So one example of this would be, for example, using beeswax as an additive, but employing a layer by layer approach when synthesizing the material. Yeah.
So we, of course, considered the health and environmental performance of all these strategies in addition to the technical performance that we just went over. We conducted a hazard assessment for all of our strategies, including our bad actor, which Annika introduced earlier as low density polyethylene. We started by looking at Pharos and the green screen for safer chemicals, and to identify hazard endpoints, and then moved on to the literature to find various studies that explain those in more detail so that we can present the main takeaways to you here in this presentation. So starting with low density polyethylene, the main concern with low density polyethylene is environmental persistence, which leads to the breakdown into microplastic particles. So we've considered, as Scarlett mentioned earlier, biodegradability and compostability were very important parameters for SWAY. So in looking at all of our different strategies, we considered the OECD 301B biodegradation test, which sets a standard for 60% carbon dioxide conversion in 28 days. And we also considered the ASTM standard that was mentioned earlier, which sets a standard for 90% conversion in 180 days. Low density polyethylene does not meet either of those standards. It is not biodegradable or compostable, and the microplastic particles pose a significant threat to human health upon consumption due to the presence of phthalate plasticizers being endocrine disruptors. So keeping with our same order that we've been presenting, we're going to look at minerals, we broke into silica nanoparticles and montmorillonite clay. So some of our main takeaways here, looking first at biodegradability. We looked at a study which looked at the biodegradation rate of a starch-based bioplastic film, which contained 0.2% silica nanoparticles, and they observed no change in the rate of biodegradation with that addition of the silica nanoparticles. So a pretty neutral metric. For us, they're on the human health side, we do have a bit of concern in terms of occupational exposure. From inhaling nanoparticles, the size of the nanoparticles is listed here, 25 to 35 nanometers. And silicosis is a fibrotic lung disease that has been correlated with the inhalation of silica nanoparticles and silica dust. This is considered a very serious occupational exposure, and we were unable to find any studies that really supported the suggestion that PPE would be effective at mitigating that. So that was something that we flagged as a significant concern. For montmorillonite clay, similarly, starting with the biodegradation metric we have here, we looked at a study that looked at the biodegradation rate of a methyl cellulose film that was cross-linked with 3% MMT. And while this film was completely biodegradable, with the addition of MMT, there was a 30% decrease in the rate of carbon conversion. So a little bit of a red flag there that it would slow down that process. And then on the human side, we share that same occupational exposure concern because MMT does contain a small concentration of crystalline silica, and it would be in nanoparticle form. The nanoparticles are much larger than those silica nanoparticles, and there is just a small concentration of that crystalline silica, but nevertheless, we're still concerned about the possibility of working with those materials, introducing the risk of silicosis to workers. So for beeswax, Emma mentioned earlier how beeswax is produced. It's naturally produced by bees, and it is therefore sustainable. That's a picture of a beeswax capped cells in a honeycomb, and removing that those wax caps is actually beneficial to the colony because they need empty open cells in order to store honey or lay eggs. So it improves the productivity of the hive. However, it is, of course, important to choose a source that promotes ethical and safe harvesting, A lot of large commercial beef farms, unfortunately, utilize techniques like wing clipping and artificial insemination to increase their output. But working with local harvesters, we should mitigate those concerns, but it is of utmost importance to make sure that we're not introducing an environmentally friendly alternative while doing damage to the environment subsequently. In terms of biodegradation, we looked at a study from 1992 that found carbon conversion rates of 67% in 28 days and 79% in 84 days. So those do meet both of those standards that I mentioned at the beginning of my section. For human health, very few red flags here. Allergies to beeswax, allergies to bees are very common. Allergies to beeswax specifically are very rare, but would cause irritation upon contact. Intestinal blockages upon consumption is a concern. And then another new area of study is the ability of beeswax and honey to actually capture pollutants from its ambient environment as it's being developed in the hive. So things like very small concentrations of pesticides or PM 2.5 being trapped in there. But it's very hard to estimate exactly how much would be present in the beeswax and exactly what concentration of beeswax would end up in the ultimate formula. So it's difficult to say how much of a hazard that is. From an occupational health standpoint, harvesting beeswax, of course, means working with bees. So the same occupational safety measures for working in an apiary are important to be employed here to ensure worker safety. Our polyester, as previously mentioned, is PLA, polylactic acid. So one of the major red flags here is that this is not home compostable. It is biodegradable with 90% carbon conversion in 100 days, which does meet that ASTM standard. However, it is not able to be composted at home. It's only able to be composted industrially. And that was something that was really important to Sway. So that was one of our major red flags here for this strategy. And then another red flag is that this is a bio-based polymer, but the degradation process still results in microplastics because it's a bio-based plastic. This is something that really hasn't been studied well, but is getting a lot of attention. In fact, the number of studies focused on PLA microplastics in 2021 was over 5-fold what it was in 2019. So it's gaining a lot of attention, but that being said, there's still a lot unknown about exactly how persistent those byproducts of biodegradation are in the environment. So it is something to be aware of. And then on the human health side, we do have just a mild hazard on the manufacturing end. Coming into contact with polylactic acid in its vapor or liquid form can lead to irritation. But there was no evidence to suggest that contact irritation in the solid form would occur on the consumer side when actually handling the polymailers. So finally, we have crosslinkers, which is our combination of chitosan and ferulic acid. One concern that came up from chitosan is that there's really not a lot of evidence that it is completely biodegradable. It's suggested, but there are really no metrics to back that up in the literature. We searched for hours. And there's also some potential concern of aquatic toxicity when it's dissolved in an aqueous environment. So that's, of course, something to be aware of and something that we would be concerned about if that was applied. Ferulic acid, on the other hand, we were able to find some good metrics on biodegradation, similar to the silicon nanoparticles that I mentioned earlier. This had no change. This when applied to a blend film of PLA and PHB. So the carbon conversion rate remained the same, and it was completely biodegradable, but it didn't impact the rate at which that happened. This one is the only compound that we were able to find evidence that there might be some skin irritation upon contact on the consumer end, and that would depend, of course, on how much ferulic acid is incorporated into the ultimate formula. That being said, it is actually very common to commonly used in cosmetics. On a topical standpoint, it has a lot of anti-inflammatory properties. I happen to have a ferulic acid serum myself, and it's fabulous. But there is that concern that there might be some irritation on the consumer end. So similar to what we did with the technical performance, we put this all in a big summary table here for you and applied the same color coding technique, obviously dark green to dark red, and the lighter green and lighter red indicating a lack of confidence or lesser confidence than their darker counterpoints. So if you look across for each strategy, some of the things that really stand out, of course, polyethylene is red across the board. We're not surprised. We're getting rid of it. The thing that sticks out most is that beeswax displays the most green just upon looking. This is similar to the technical performance table that we showed earlier. One of the things that we're most excited about the beeswax is that very confident biodegradation metric, which is one of the most important parameters for sway. So this really showed, beeswax in particular showed very promising health and environmental performance in addition to the previously mentioned technical performance.
All right, so wrapping some things up and just going over what we've previously mentioned, our team feels that beeswax is our #1 most promising strategy. However, once again, this approach should be considered in the realm of the other strategies suggested. That way we can hopefully see a synergistic effect between the positive improvements. And our recommendations for sway are to further research combining these strategies as previously mentioned, explore different synthetic strategies. One of them was previously mentioned, the layer by layer synthetic approach. Further explore the occupational and engineering control measures that can be employed to lessen the adverse effects from inhalation of nanoparticles and mineral dust. And then lastly, a broader view into biodegradation byproducts, particularly from the mineral standpoint, and reassess home compostability to make sure it is completely in line with sway's target when employed in the final solution. What's up?
I have a quick logistical question. So you mentioned how beeswax can be responsibly sourced, and it's actually beneficial for them because it gives them space to do their thing. How is beeswax normally removed from a hive without human interference?
It's not.
Okay.
That they build more hive. So that's the main driver for expanding a hive. The way that it's removed is very simple. It's especially if you're working in an apiary where your honeycomb is sort of in a frame and very easily accessible. It's the quickest, just a little slice, takes it right off, and it takes about 5 seconds, and you put it right back, and they get right back to work. Yeah.
Thank you so much for this talk and for the contributions of I'm curious if you have any so the layer by layer approach that you were looking at.
Sure.
Do you have any sense of how being comment on degradation behavior on such films? Do you have thoughts about that? Did you talk about that when you did research on that?
That's a good question. I didn't find any compostability or biodegradation metrics when the layer by layer approach was utilized, and that is something that should be further explored, especially as they suggest that it creates a denser film, meaning that water vapor permeability is going to be lessened, and therefore biodegradation may be lessened.
Yeah, I think it's super interesting because many materials today on the market too, they have, you know, they're laminate structures by definition, but it's almost like you have a small coating on each side. So like many of the cellophanes that are used, PVDF coating on each side, and you know, definitely the core is degradable, but you know, how does that kind of laminate structure affect the biodegradation? It's very interesting.
Yeah.
You know, so that's the kind of approach that comes to mind when you look at what you're suggesting.
Sure.
Interesting.
You mentioned sort of the maybe inconsistent nature of the final product with beeswax. Do you think that that is in conflict with the actual usage, or would it be okay to have like kind of a lumpy polymailer?
I was thinking about that and I was like, if I ordered something online and it came in a package that was kind of lumpy, I wouldn't care. Yeah.
Yeah.
No.
And our takeaway as well was, I believe it
It
still
didn't-
improved mechanically.
The performance.
And do you think the layer by layer approach would mitigate that at all, or is that not related?
That was
Um,
not related.
Yeah,
But
at
maybe.
best, we could say potentially, depending on if the layers are oriented in a certain way where the lumpiness would be on the interior, so it doesn't have to, the consumer doesn't have to be afflicted by that.
That being said, whatever you're picturing, I will like to put lumpiness in perspective. It's not like clumps.
Yeah.
It's
Yeah,
like,
and I'm sure we're
very
talking like the
minor.
micro scale.
yes, yes.
Yeah, you
it's-
would even.
Also, a big consideration with all of the additives that we're considering is the percent that you add is going to affect all of these. So I
Sure.
think that one recommendation we have is studying the general percents. And so the smaller the percent, also that would mitigate the macro scale.
Definitely.
Sure.
So seeing that, you know, all these three projects today talk about some element of over engineering and how kind of like, you know, the rules are set by a material that's superior. And now we're trying to be better because they didn't have to worry about that, right?
Yeah.
So is there anything you can say doing all this research about the suede part of it? Are those reasonable in your? Or
That's a good
come from
question.
that? Like, do you experience anything like, oh, because, you know, obviously compared to LDPE and some over engineering, but is there anything you can highlight? If you look at all these parameters. Yeah, is there anything that comes to mind?
Oh, it's going on its own.
Maybe
There you
think about this might not be important.
What about like the elastic modulus? Maybe that is a little bit on the high side for Sway's story.
Mhm.
Because like if you look at LDPE, it's much lower.
Yeah.
Yeah, another thing which is probably an issue with me needing to inform myself more about it, but strain up breaks seem to be a bit harder to reach for some of these. Oftentimes when we saw strain at break decrease, we saw the tensile strength increase, most likely just due to lower chain mobility. This is something that I'm not sure if it can be reassessed. As I understand, the strain at break does give the material some flexibility, but I'm not sure how much that's necessary when considering packaging design. Yes.
Thank you.
Sorry, Amanda.
And I was just, yeah, this is a comment building off of that,
Yeah.
about like the comments about like strain up break and
Sure.
moisture barrier, and it's very common that these two like come at a trade-off for reasons that they mentioned in their presentation, right? Like when a polymer has more chain mobility, that means water molecules can probably move through that chain a lot easier. So it's kind of like these two things are kind of at that a little bit, and so it's about like finding those balances and finding those like breakout points like we saw with beeswax, where maybe you can improve both, right?
Yeah.
For sure. Andrea.
I was just gonna ask, like, my only comparison to this is those like beeswax wraps that like we wrap your food in.
Yeah.
But I know that those are pretty affected by like heat, like the whole point is that like the heat of your pants like seals it off, so like, what were you guys thinking of like these mailers using beeswax as a coating on like days where you didn't truck or something?
Yeah, we considered that, and that was one of our major concerns, which is why we pivoted to beeswax as an additive, not a coating. You're correct that beeswax is a coating in those products, and we looked a lot at those food packaging examples that are already on the market. I own some, they're great. But the heat, we incorporating it as an additive versus a coating, we seem to find evidence that would mitigate its sensitivity to heat, especially in a lower concentration, depending on the percent added.
That's neat, and probably the other stuff, like the other strategies in combination would probably help with that.
Yeah, sure.
Thank you, taking another round of applause.